Welcome everybody to this online version of the lecture. So today I am casting, I think that's what you kids call it, I'm casting from beautiful Houston, Texas. You can see Houston, Texas behind me to prove that I in fact am in Houston, Texas. As a result of that light behind me though, you can't see my face, and we're probably all better off having it that way. So today we're going to talk about source transformations. This is still part of chapter 4, so the first part of chapter 4 that we did, we were going over ways to solve for unknowns in a circuit by using a method that minimizes the number of equations that we have to solve. And those two methods that we learned previously in chapter 4 were node voltage and mesh current techniques. The source transformations is another way that we can take complex circuits and make them simpler. In particular, we can make them simpler when trying to solve for an unknown in our circuit. The big difference between the node voltage and mesh current methods that we talked about and source transformations is source transformations are really intended for when you're only concerned about some unknown in one region of the circuit. And that's actually fairly common. That's situations where, like, you are connecting a resistor value to two terminals of a circuit, and you want to see how that resistor value impacts the rest of the circuit. So source transformations are very good for things like that. What they're not good for is for finding out every unknown in your circuit, which is what mesh current and node voltage are for. So with source transformations, you're going to basically be transforming, and by doing so, sort of eliminating the previous structure of a circuit. You're going to build equivalent circuits, but just like in the case of combining resistors, once you combine those values, if you want to solve for something from some previous iteration of the circuit, you have to then unpack the circuit and do a series of kind of voltage and current transformations to unpack it. So, but normally, if you want to know everything about a circuit, use one of the techniques we've already talked about. If you want to know something about a load connected to a circuit or about the impact of a particular value on a circuit, that's where source transformations are going to come in handy. And also what we talk about after this is going to be, after this we're going to talk about Thevenin and Norton equivalent. That also is mostly useful for when you're looking at the impact a circuit has on some single external connected load, or when you're looking for the impact that load has on the other circuit. So, okay, so jumping into source transformations. The basic idea behind source transformations is that we can take to do this, I'm just going to go through the notes. I'm just going to use the notes on the screen. I was going to try drawing stuff, but I draw bad enough as is. You don't want to see me drawing on a laptop. So the idea is anytime we have a voltage supply in series with a resistor, we can transform that into a current supply in parallel with a resistor. Now, a lot of times people ask, well, if it's only a voltage supply in series with a resistor and a current supply in parallel, and also the transformation can go the other way, a current supply in parallel with a resistor can be converted to a voltage supply in series. Sometimes people say, well, why not? What about the case of a voltage supply in parallel with a resistor? Well, a voltage supply in parallel with a resistor is usually a very easy thing to deal with anyway, because if you place a resistor in parallel with a voltage supply, all you're doing is burning up current through that resistor. The voltage is still the same. So a voltage supply in parallel with a resistor is basically just a voltage supply. And similarly, a current supply in series with a resistor is just a current supply. So those two cases are not as interesting. They're not as necessary to have source transformations because we already basically know, current supply in series with a resistor is a current supply. Voltage supply in parallel with a resistor is a voltage supply. So the transformations for those are easy. So what's this relationship? How do we have voltage supply in series with a resistor to current supply in parallel with the resistor? Well, it's fairly straightforward. It's the magnitude of the current supply. The magnitude of the current supply is going to be Vs divided by R. And you can guess in the other direction, if we have a current supply in parallel with a resistor, the voltage, the Vs is going to be Is times R. So we just multiply that. And it should also be noted that the resistor value stays the same. When we do the transformation, the resistor value stays the same. So pretty easy, pretty straightforward. The biggest thing that people mess up with when applying this technique is you have to be very careful before you do source transformations to know that voltage supply is in series with that resistor. A lot of times people, when doing these source transformations, the biggest mistake they make is they see a voltage supply and a resistor, and they say, oh, those two things are in series with each other, when in fact there's not. If there's some other resistor connected here, like right here, if you can see this on your screen, if there's some resistor connected here, then this voltage supply is not in series with that resistor. And similarly, if there's a resistor up here, there's a resistor up here. This current supply is not in parallel with this resistor. So the main thing is make sure you have a situation where the voltage supply you're dealing with is in series with the resistor you're dealing with, or the current supply is in parallel with the resistor you're dealing with. Okay, so how can we, So I'm going to skip the proof of this for you. You can go back and do it later, and maybe there might be a question on the homework. I don't quite remember. There might be a question on the homework that asks you to prove it. But let's just go ahead and just start looking at an example of how we could simplify a circuit with source transformation. So in this case, we have a fairly large circuit, a big collection of voltage supplies, current supplies, and resistors. Of course, like every other circuit in the Nielsen book, this makes actually no sense in practice. And we have a resistor over here. We have this 8 ohm resistor. And our question is, what's the voltage across this resistor? And again, like I was talking about, that's a critical part about source transformations is we're looking for one unknown in the circuit. In this case, the voltage across one resistor. So if the question we're asking, what's this current and what's this voltage here and what's the power for this guy, if there was a lot of questions all over the circuit, it's probably best not to use this technique. Okay, so let's start by looking at this thing. So let's start by looking at the circuit, and we can sort of see how can we do transformations to simplify this. Well, one thing I see here is I have a current supply in parallel with a resistor here. They are, but there's no other resistors here. This current supply is in parallel with this resistor. What I can do is then, I have here a voltage supply in series with a resistor and a voltage supply in series with a resistor. What if both of these are converted to current supplies in parallel? Then I'll have a whole bunch of stuff in parallel here. I'll have 3 current supplies in parallel with 3 resistors. And once I get there, I can combine them. You can just remember back to chapter 2 or 3 or whatever it was, that current supplies in parallel add, voltage supplies in series add as well. So we just have to be careful with the orientation of those when we're doing that. So if we look down here, so this transformation, so a 120 volt supply in series with a 20 ohm resistor, that's going to convert, to do the conversion, we do 120 divided by 20, that's 60. So it makes a 60 amp current supply here. And then that 20 ohm, instead of being in series, it now becomes in parallel with that supply. Same thing here, we have a 60 in series with a 5, that current supply is going to be 60 divided by 5, that's going to be 12. Now be careful here because the orientation, the positive side of this voltage supply is oriented on the lower side of the supply, which means when we convert it to a current supply, that current supply is going to be pointed down. So the conversion is always the arrow of the current supply is always oriented pointing towards the positive side of the voltage supply. Okay, so then after we do this conversion here, we have our, 60 divided by 5 is 12, that's how we get our 12. It's pointed down because the voltage supply was oriented positive side down. That 5 ohm stays a 5 ohm, but we move it to be in parallel. So now we have down here the 6 amp, the 12 amp, the 36 amp, all in parallel. And we have these resistors, the 20, the 5, and the 6, all in parallel. So now we can combine these. We have 36 up, 12 down, 6 up. So our total current flowing up in this circuit is 42. Our current flowing down is 12, so the total current supply here is going to be 30 amps. So in fact, we have that here. We have 30 amps here. And so we can do this conversion. The 30 amp supply pointed up. We have a 20, a 5, and a 6 in parallel. That's easy enough to convert. We just convert those the same way we would any parallel combination of resistors. So doing the math on that, and again, the math on that is the inverse of 1 over 20 plus 1 over 5 plus 1 over 6. And that is 2.4 ohms here. So now we're left with a current supply and in parallel with a 2.4 ohm resistor. And we could say, this circuit is simple enough that I could probably solve now for the voltage across the 8 ohm. How would I do it? I could just do a current divider here, right? Combine so 1.6 and 8 is 9.6. I can just do a current divider on a 9.6 branch and a 2.4 branch. But we can go even further. We can make this even simpler using another source transformation. So if we, once again, take this current supply in parallel with a resistor and convert it to a voltage supply in series, now this time by multiplying, so the 2.4 gets multiplied by the 30, so that is going to be 72, so it creates a 72 volt supply, and now this 2.4, rather than being in parallel, this 2.4 now is in series. And now you can see this is much more reduced here. Now we can simplify this even more by combining the 2.4 and the 1.6. So that's going to combine into a, what's that going to be? A 4 ohm resistor here. So in that case, we have a 72, a 4 ohm, and an 8 ohm, and that's a very simple voltage divider. Yeah, 72. Well, in this case, we just do it by solving the current and then using the current and Ohm's law, which is how we derive voltage divider. But basically, you could just do this as 72 times 8 divided by 8 plus 2.4 plus 1.6, and you're going to get a total of 48 volts across that thing right here. So, was that faster than doing a node voltage and mesh current? In this case, it probably was, maybe. So let's go back. Let's go back and look at the original circuit. Well, it's got one essential node. We probably could have solved this fairly quickly using node voltage. Certainly is better than mesh current. But a lot of times this is a technique that's going to help speed things up. So when you're solving for one unknown. And when are you going to get a smallish abstract circuit where you're solving for one unknown? On the FE exam. So this is kind of a FE exam prep thing. And the main thing though, and I want to go over some techniques because I'm going to stop this video. This video is going to be a short one. We're just going to do source transformations. And I want to just go over some techniques when doing these. So in addition to the technique that I talked about of making sure that the voltage supply is in parallel, or the voltage supply is in series with the resistor and the current supply is in parallel with the resistor, in addition to double and triple checking that that's actually the case, the main thing to know with source transformations is if we're solving for, a resistor over here, like we're trying to find the voltage across a resistor, we always want to start doing our source transformations as far away from that as we can. We want to go all the way to the other end of the circuit, whichever way the circuit's oriented. We want to go all the way to the other end and start doing transformations there. If we start doing transformations close to where we're solving, rather than folding up the circuit from the other side, we can easily get in a situation where we trip ourselves up, where we combine things that aren't in series or something else like that. It's almost always easier to just start on the other side of the circuit from wherever we're trying to solve for our unknown. Start folding in the circuit, start compacting it, start doing source transformations, simplify it there, and then work our way towards our resistor of interest. And then how far you want to push it to solve is usually up to you. So if you have a test or a quiz and I say solve for this voltage using source transformations, if you had gotten here and you'd done current divider, that'd probably be just fine. So whether or not you want to go this extra step, that's kind of up to you. So what are source transformations good for? They are good for, as we said here, finding an unknown in the circuit. What are they bad for? They're bad for things like finding the total power in a circuit. So source transformations, even though you are finding an equivalent circuit in terms of how it affects something else in the circuit, by eliminating these, by combining these, by reducing these, you are quite often missing, you're missing the overall power in the circuit. So anytime you're solving for overall power in a circuit, doing these series of source transformations is not going to be helpful, because essentially you're going to be getting rid of the thing you were trying to solve for the power for. So overall power, those sorts of things, you got to just do those the old-fashioned way, doing a mesh current or a node voltage, and then just calculating the power for every source or for every resistor. So, but for now, I'm going to leave the topic. That's going to be the end of the topic now for source transformations. Source transformations are very handy. They kind of come back every once in a while. It's kind of an interesting thing. They'll definitely sort of trickle into the work that you do throughout your educational career and probably your career thereafter. So it's important. But there's not really that much to say about it. It's a fairly simple transformation, and you'll get to do examples of it in the homework. So thanks for watching this video, and stay tuned for the next one.